All right, so this next session, next talk will be by Manish Jain, and he'll be telling us about phonons in these twisted Moiré.
All right, first of all, I'd like to thank the organizers for giving me this opportunity, and I apologize to every one of you because one of the things I didn't do, or I thought I did, is send them my title, the title of the talk. So apparently it's not on the website, and that's probably just me not sending this thing in at all, or thinking that I've already done it. In any case, I'm going to be talking about phonons in Moiré materials. So here's a brief outline of the things I'm going to be talking about. We've heard a lot of things about electronic structure in these twisted TMDs, for example, in Abhay's talk just before this one. But there's also some very interesting things that one can do with phonons in these materials, and that's one of the things that we'd like to that I'd like to focus on. So I'll talk about low frequency phonons in TMD bilayers, the Raman active modes in twisted WSE2, the same material that Abhay was talking about, and Raman line width in the G mode in twisted bilayer graphene. So, okay. So as we have all seen, twist is a very interesting degree of freedom. And most of the time people are interested in the flat bands that originate from twist and all the associated electronic properties that come with that. But there is also some very interesting things that happen when you twist two materials. For example, you see these super lubricity. This is seen in graphene. When you take one piece of graphene and rotate one layer of graphene and rotate it with respect to the other one, at some point the coefficient of friction becomes nearly zero. And of course, there are all these by now very well known domain wall networks and topological point defects in these systems. And so the question that we are sort of asking is, this is structural, this must have some origin in some phononic kind of properties as well, is how does twisting actually affect the phonons in these materials? Since Abhay has already given an introduction to TMDC bilayers, let me just briefly say what are the kinds of structures that you form when you twist one layer with respect to another. If you take a TMD bilayer and you rotate with an angle close to 0 degrees, then you get one kind of stackings, which is the AB and the BA, which are essentially the same stacking, and these are called the 3R stacking, if you wish. And then there is this AA stacking, which is nominally unstable. On the other hand, if you go near 60 degrees, you actually see a different kinds of stacking, which is the AB prime and the A prime B, and the 2H stacking, which is the natural bilayer of TMDCs. Okay. Now, if you just construct these structures and you start asking the question, okay, if I let it relax, then what really happens in the system? What really happens is the following. I'm showing you, sort of a calculation of the interlayer separation landscape. So we're just looking at the interlayer separation, and we are just going as a function of angle. As the angle becomes smaller, and as you're going closer and closer to 0 degrees, what you notice is that, we know that the Moiré length increases. But what is also quite striking is the fact that it increases only because some regions of the high symmetry, some high symmetry stacking regions actually increase in area. The unstable stackings, which is this AA stacking, it actually doesn't increase in area as uniformly as the separation increases, right? So essentially what you get is these domain wall networks, which are very well known, and as the angle decreases, all that happens is the area of this stable stacking keeps increasing. Now, this is near 0 degrees in TMDCs. If you go near 60 degrees, you basically get a slightly different looking picture. It's more or less the same, except one thing that is different about near 60 degrees is that these two stackings are not the same. I don't know if you can see it very clearly. There are two dark blue triangles here, if you can see. So these two dark blue triangles are not exactly the same area. One of them is larger than the other, and as a result, these domain walls sort of are curved with respect to, they're no longer straight. And this can have some interesting consequences on if you make these domain walls curved enough, at some point you would think that because these cost energy, that the system might reconstruct, and that doesn't seem to happen in many systems over here, but I think if you tune strain and stuff, you can probably make a Moiré reconstruction happen in these systems. Okay, now the interesting thing to note here is that some of these stackings are actually unstable. Okay, so if you were to try to make this experimentally, you would not be able to make it. It would not stay there. Whereas the AB and the BA are actually stable stackings. And similarly here, the AB prime and the AA prime are the stable stackings, but the A prime B, which is these red triangles, these are actually unstable stackings. Yeah? Okay. So now the thing that we would like to do with the structural stuff out of the way, the question that we would like to ask is, how do I go about calculating phonons for the system? I'm a theorist, so I do calculations. So the question that we are asking is, how do you go about calculating phonons in the system? Now, you can, of course, construct a geometrically commensurate superlattice. Real lattices may or may not be commensurate, of course, but you can find something which is close enough and say, okay, that's probably going to have similar properties. The problem is, these systems, if you construct them, the superlattice will have tens of thousands of atoms in them, right? So there is no possibility of doing a first principles phonon calculation on the system at all, right? So the next best thing, there are many possibilities. One is you could write a continuum theory for this. That's one way to go about doing this. The other possibility is you can actually go to these interatomic force fields. Right? Interatomic force fields there's an atomistic description, but there are no electrons. The electrons have all been integrated out. We only have forces on the atoms, and that's essentially all we're going to work with. Now, one thing that you have to make sure that this force field does correctly is because in a given stack, in a given structure, you have multiple stackings present simultaneously, right? So you want to make sure that the force field that you use actually describes all the stackings correctly. And for that, people have come up with these. Kolmogorov and Crispy had given a prescription of how to construct such a force field. And there are many others. There's something called drip, there's interlayer potential, and many others, right? And one thing that you have to make sure is that you use any one of these methods, because then you're guaranteed that all stackings are described properly in your system. Then, of course, is the problem of, fine, you have the force field. So in principle, you can construct dynamical matrices. But you still have to construct them and you have to diagonalize them with these force field that you have. And for that, we've actually written a code called PARFORM. It stands for Parallel Phonon Calculator for Moiré Systems, which is going to be available soon. Essentially, what it does is it takes these force fields, which are fed into a software like LAMPS, which is very often people who do these kinds of calculations they use. It will then calculate the dynamical matrix, the force constant matrix from there, and Fourier transform it for you. These matrices can be large. If you have 10,000 atoms, then your matrix will be 30,000 by 30,000. So you need a way of diagonalizing it and so on and so forth, which is all done in this package. Okay. So let's say you did all of this, and then you did the calculation. This is what you'd get, right? I don't know about you, but this is spaghetti. Right? That's all. I don't know how to make sense of this. Right? There's a lot of phonon bands that you get, and you have to now start to ask the question: how do I make sense of this? Right? This is too many phonon. This is done for 2-degree twisted bilayer WSE2. Right? So the thing is, in principle, once you go from here, you know this is good. You knew this was going to happen, because if you have n atoms in the unit cell, or in this case the Moiré cell, then you have 3n bands at every phonon bands at every k point. Now, what you cannot do is you cannot try to analyze them in the standard way in which you analyze, let's say, your phonon bands in a unit cell with let's say 3, 4, 5, or 10 atoms in it, right? One thing that you immediately realize is the Moiré lattice doesn't have the underlying symmetry, may not have the underlying symmetry of the unit cell lattice, in which case you have to characterize this. Even if you wanted to do it with group theory, you would have to characterize it with a different group, which is fine. But even so, there'll be too many bands. And I'm not sure what you'd gain by doing that, right? Let's say you even did that, it would still be a large number of bands. The thing to realize is that the Moiré lattice is by and large constructed of a folded version of some kind of each layer, of course, is a folded version of its, because it's a supercell that you've constructed. So one way in which you can identify the Moiré modes is by recognizing that these are folded versions of, let's say if you're interested in Raman active modes, these are folded versions of the Raman active modes of a bilayer. That's one way in which you can sort of try to analyze all of this. Of course, these are not just the simple bilayer modes of the individual layers. The two layers are talking to each other. That's the whole reason why this is all very interesting, right? So a simple way in which you can try to understand what is, let's say if you're interested in comparing this with Raman spectra, is by projecting these modes onto a bilayer-like mode, and I'll describe what this means in a minute, by projecting the Moiré modes that you get onto such modes and then try to see if you can make some sense of that. Okay, so this is sort of the general program that we're going to follow. You could come back and you could say, look, in principle, what one could do is actually calculate the full Raman tensor, right? You could actually calculate the Raman tensor and the Raman tensor will tell me what is Raman active. I don't have to decide a priori how to do any of that. Problem is it's a third derivative of the susceptibility. It's pretty hard to calculate. So this is sort of a poor man's alternative, which is you say, I know that the bilayer mode was Raman active. So if I project onto that Raman active mode, maybe I get something which the experiment sees. Okay, so with this program, let's start thinking about low frequency phonons in TMDC bilayers. Okay. So as you are all probably very familiar with this, a monolayer of course has, if you look at just the low frequency part of the spectrum, this is frequency versus wave vector. You have three modes here, the out of plane vibrations and two in plane vibrations, vibrational modes, the longitudinal acoustic and the transverse acoustic modes. Now what happens is when you put two layers together, you still will have only three modes at q equal to 0, but the second layer also had these acoustic modes and they sort of hybridize and you start getting these the layer breathing and the shear modes. Essentially you have 6 modes now. 3 of them are gapped out, right? 2 of these are shear modes, which refer to these sliding of the 2 layers with respect to one another, and one is a layer breathing mode. Okay, and if you look at the eigenvectors corresponding to such modes, essentially these are just relative displacements of the 2 layers with respect to one another. Okay. Now, if you want to do this for let's say this is done for MOSE2 as a function of angle, you start seeing something quite interesting. So this is a busy slide. Let me take you through this. Essentially, what we've done is we've calculated the full phonon spectrum, and the phonon spectrum, as you might expect, is a mess. So to analyze it, we have projected all the modes onto these modes that I just showed you before, onto these shear and breathing modes. And I'm just asking, what does that projection weight look like, right? So I've calculated this projection weight, and I've plotted this projection weight as a function of angle and as a function of frequency, right? So what you notice here is, you notice something very strange. First of all, you notice that this is shear and layer breathing modes, right? You notice that there is a mode which is at very low frequencies, right? Typically, when we do solid state physics, we tell our students there is the acoustic modes, and the acoustic modes are the only ones which are actually 0 frequency. But now I'm seeing some other mode which is shear-like, because the stars here refer to the shear-like mode. That is also very low frequency. Okay, so I call this ultra soft, right? Its frequency is less than 1 centimeter inverse. So 1 centimeter. So in region 1, you see these shear modes with frequency less than 1 centimeter inverse, and you see sort of an averaged layer breathing mode. Okay. Then when you go to region 2, you see an ultra soft shear mode. You also still see this mode, but now you start seeing that there are multiple of these layer breathing modes. So the circles here refer to the projections onto the layer breathing modes, which is basically I'm doing projections onto this. So I see multiple of these, but there's one shear mode. And then all of a sudden, as the angle becomes smaller, I start seeing these other shear modes appear as well. Yeah. So the thing is, okay, so you see what you see, but is this related to reality? It is. I mean, this we are comparing it to experiments. The green stars and dots are experiments, and the circles are the I don't know, brown or orange circles are calculations. and they're roughly in the same ballpark. So, the frequency, the numbers are not exactly precisely the same, but these are they're really close. So qualitatively, we are getting the right physics. So the question now you can ask is, the strangest part about all of this is, what are these low frequency modes? What do they correspond to? So when you look at this low frequency mode at a large angle, you start seeing, and I don't think you can see the arrows, but all the arrows are pointing in the same direction. So if you look at an angle, so let's say about 23.5 degrees, and I look at this low frequency shear mode, right? It is this mode, right? It's zero frequency. It doesn't cost any energy. And at larger angles, you start that this mode is actually starting to localize. And actually, if you notice carefully, these modes are actually localizing at all your domain boundaries. So first of all, you ask yourself, why are these modes zero frequency? I mean, when I look at a bilayer, these shear modes actually cost energy, as they should. Why is this not costing any energy? The simple way to understand this is to just to realize the fact that in a Moiré cell, I already have all kinds of stackings present, right? So when I shift one layer with respect to, when I shear one layer with respect to the other, I still have exactly the same stackings, more or less, right? Which means, in some sense, the cost of doing this is almost zero. Energy cost of doing this is actually zero. And this is actually this is actually well known. This is what is called a phase-on. This is called a phase-on mode. And this is essentially what is responsible for us seeing these nearly zero energy modes in these systems. Okay? But what about at higher angles? You again see these modes which are zero energy, and you start seeing that, look, they're localized on these domain boundaries. And let me see if I can show you what the motion of one of these modes might look like. So this is just the eigenvector of one of the modes, which is zero frequency. And I don't know if you can see, but if you notice here, this seems to be shifting, right? So this is sort of an effective Moiré lattice, the acoustic mode of the effective Moiré lattice, which is showing up. This is basically nothing but a phase-on mode. This is a phase-on mode which is associated with the Moiré lattice, which is showing up in this. I hope everybody can see that it's the whole the center of that thing is moving left and right, right? Okay. So these are two sort of new and interesting modes which have shown up, which are almost zero energy. And then you ask yourself, well, how many such modes are there? And it turns out, when you look at, and this is not related to your twist angle, in the sense that even near 60 degrees, you see exactly the same things in MOSE2. And I believe it will be true for graphene and any other material as well. This has nothing to do with the TMDCs that we actually studied. In fact, in all of these modes, you start seeing that these are not exactly zero, right? But these are they're slightly gapped out right at the end. I mean, this scale is 0.4 centimeter inverse. This inset is plotted with 0.4 centimeter inverse, right? In some cases, they are below. That's a numerical artifact. We believe that it is slightly negative. I mean, it's minus 0.02 centimeter inverse. It's probably just a numerical artifact of our calculation. But by and large, you're seeing all the acoustic modes, and then you see suddenly these modes, and you see them, they turn around right at the end. So they are gapped out, but they're gapped out at 0.2 centimeter inverse of that order, which essentially is zero for all practical purposes. Yeah. They are Goldstone modes. They are indeed Goldstone modes. And I'll explain in just a minute. So these are ultrashort modes, which are optical modes. So at least in how we see it, and this is related to the fact that we've only done commensurate structures. So the physics of this actually is related to the fact that if you go to, let's say, the Frenkel-Kontrova kind of a model, which is just a simple model of, let's say, if I have a potential with a length scale B, and if I have, let's say, beads and springs with a length scale A between them, and if I make A and B incommensurate, then it is well known in the system, as long as A and B form an truly incommensurate structure, then a gapless phase-on mode will show up at omega equal to 0, which is basically a Goldstone mode. But if I make this thing commensurate, which is what we've done in all our calculations, right? So then this mode actually gets gapped out, but the gap is extremely small. So unless we are measuring things at very, very low temperatures and you can actually see that difference, it's probably not going to matter for most practical purposes. Yeah. Okay. I mean, that's sort of related to the fact that, if you don't have all stackings to begin with. In an incommensurate structure, you really had all stackings, right? This is a finite system, which is periodically replicated. Okay. So that's all good and well. So what? So, one of the things that you find very, very interestingly in these systems is that you see that there is, if you plot frictional force as a function of misfit angle, and I think this is done for graphene or graphite-like structures, you see that the friction is only present when the angle is really small. Of course, they have a resolution of only 5 degrees, which is pretty good for experimentally. I can imagine doing this experimentally is much harder than doing it on a computer. Nevertheless, you see that it increases, but otherwise the frictional force is extremely small. So we think that this is related simply to the fact that the moment these shear modes, once they start splitting from this phase-on mode and they become more like your when they gap out by substantially when they go to actually the full shear mode frequency, that's essentially where you will start seeing this transition from a super lubric behavior to a sort of a pinning behavior. A simple way to understand this is to understand this in the following way. Imagine if all your stackings are roughly the same size, and there is no development of these large regions of AB and BA stacking, then in some sense, shifting this one layer with respect to the other will not cost you much energy. But on the other hand, the moment these regions develop and become large enough in area, then all of a sudden, when you shift in this area, there's a cost to actually shifting one layer with respect to the other, and so you should actually have some pinning kind of behavior that should happen. And this happens roughly at the angles when this happens when the shear modes actually split off and become from the zero energy phase on mode, they actually become finite in frequency. You can also look at this in terms of a potential barrier. If you take such a system and you sort of slide one layer with respect to the other, as the angle becomes smaller, the barrier to doing this becomes smaller, and you can also understand it in that way. Okay. So now let me quickly move to the second thing that I wanted to discuss, which is Raman active G modes in twisted WSE2. So this is driven mostly by our experimental colleagues who from Anindya and Ajay Sood's lab. They measured a large number of twist angles near 0 degrees, and they saw that if you look at the G mode Raman frequency, that it seems to split, right, as a function of angle, and then the split sort of goes away. It becomes less as a function of angle. So what we wanted to do was try to understand how do we make sense of this data as to where is this split coming from. So this is their data plotted in the way that at least I look at it, which is that there's a Raman shift. There are two peaks which they have fitted to their Raman. This is the EG peak. They have fitted two peaks to it. And if you look at the positions of the two peaks and you look at the difference between them, the difference seems to have this kind of a behavior. So we're going to follow the same program that I told you about, and in this program, essentially what we're going to do is we're going to calculate the phonons, but there are too many. So we're going to project them onto the G modes. So, but I don't know how to define a G mode I know how to define it for a unit cell. I don't know how to define it for a twisted bilayer system. So I'm going to make it up, right? Hopefully you'll agree with what I made up. So I know what a G mode for a bilayer looks like. It looks like this, right? All the chalcogens moving in one direction and the opposite direction in the other layer, and the let's say in this case tungsten atom moving in opposite directions as well. So for the twisted bilayer, essentially all I'm going to do is put this displacement on one layer, put this displacement on the other layer, and then just put them together. Okay, that's what I'm going to define as the G. Now I'm going to call it the EG-like mode, right? Because it's not clearly not EG, because this would have been EG only in the case of a unit cell with 6 atoms. But nonetheless, it seems like a reasonable thing to do, at least to us. But now the thing that we are after is the splitting. So how are we going to get at the splitting? So if you look at, let's say, this the interlayer separation landscape, you notice that there are many different kinds of regions, which I discussed before. So what we're going to do is we're going to take the Phonon eigenvectors that we get from our calculation at the gamma point, and we're going to project it onto different layers, right? And then try to see if the eigenvectors have different, have more weights in different regions, and maybe that's the reason why the split. So the idea is maybe the AB and BA regions have a different phonon frequency than, let's say, the AA regions, and essentially when you measure both of these simultaneously, and that's the reason why you're seeing this difference. Okay. So when you do the projections, and there are many phonon modes, so I've done the projection for all the phonon modes. This is as a function of angle. You see that indeed we are sort of seeing an increase, as a function of angle. As the angle becomes less, the separation seems to increase, and then it seems to decrease. Okay, but now, if the idea that we had is correct, that if these are coming from different regions in space, then we should indeed see that this total thing that we are seeing over the entire sample is actually really coming from different regions, and there are different distributions in different regions. So for example, in this SP region, which is nothing but your domain wall kind of region, you do see that there is a different distribution than, let's say, in the AB and BA regions as they develop, and in the AA region. So we think that the reason why this is splitting is indeed because of this very simple reason, that as your angle becomes smaller, that these regions become larger, the AB and BA regions become larger and dominate your Raman spectra. Whereas when the angle was larger, these regions are all almost equal in area, and as a result you measure an average quantity, and that is sort of the reason why this thing goes up and then starts going down. The splitting goes up and then starts going down, because eventually if the angle becomes really small, right, the Raman signal will be dominated only by the AB and the BA regions, because those are the only ones that are growing, whereas everything else is not growing in area, and so as a fraction it is becoming less and less. So that we think is the reason, and indeed if you forget all of that and you say, okay, look, let's just calculate the difference, you've done this, you find that indeed it follows a similar trend. Yeah.
Basically what you're saying is that via the optical phonon you're measuring the gapping up of the phasons.
This is the EG mode. This is the EG mode. This is not the, this is 200 centimeter inverse. Yeah.
Measuring the interaction of the EG mode between the two layers, which is the same mechanism as the phasor mode.
That is sort of correct. That is sort of correct. But the EG mode is high frequency, but you're absolutely right. The two layers, the chalcogens are indeed moving opposite. Of course, the tungsten is moving in the opposite direction, but maybe that doesn't matter. Yeah, in that sense, you're absolutely right. Yeah. That's actually an interesting, I hadn't thought of that. That's an interesting way of looking at it. I hadn't thought of it in that way. But that's an interesting way of looking at it. So yeah, so this might essentially refer to the sort of the splitting of the phazon mode in some sense. Yeah. Okay. So now in the last 10 minutes, let me quickly talk about the Raman line width of the G mode in twisted bilayer graphene. So in twisted bilayer graphene near magic angles, there have been many interesting experiments electronically, but there's also some very interesting Raman experiments where they show that the Raman line width is much higher compared to what it would be for, let's say, an AB stack graphene. And in general, in twisted bilayer graphene, it is believed that the electron-electron interactions are perhaps the most important effect. But people do worry about electron-phonon interactions in these systems as well. And so what we wanted to do was sort of get a sense of how important are these electron-phonon interactions. And one way in which you can think about this is, if the Raman line width is increasing, I mean, it is coming from the electron-phonon interactions, and that sort of gives you some idea of how important such things might be. So what we thought about is if we could calculate the electron phonon, the Raman line width in twisted bilayer graphene, and line width in general, if you follow simple Matheson's rule, you should have a line width that comes from electron phonon coupling. There should be some line width that comes from phonon phonon coupling and from disorder, right? This is the hardest one to estimate, so we are not going to do it. We're just going to do both electron phonon and phonon phonon estimates of the Raman line. So now, unlike the phonon program that we followed, which we still will follow, we have to do something about the electron phonon coupling. We have to calculate the electron phonon coupling. So to do this, what we're going to do is we're going to calculate the electronic band structure using an atomistic tight binding model, right? With distance dependent Slater-Coster parameters. So our Slater-Coster parameters are now going to be distance dependent, and you'll see in a minute why we're going to do that. To account for some electron-electron interaction, we are going to include them only up to the Hartree level, not the Hartree-Fock level or anything beyond that, just the Hartree level. And we are going to follow the same program that we did for phonons. Now, the reason why we made our electron phonon coupling, our tight binding parameters distance dependent, is because then we can take the derivatives. Right? And once we can take the derivatives, you can actually just define your electron phonon coupling matrix element in this way, where essentially all the ingredients that go in here are either the phonon eigenvectors or the electronic eigenvectors or the distance dependent transfer integrals for whom we need to take the derivatives. So once we've done that, we actually get the electron phonon coupling matrix elements. This is easier said than done. These are very large number of elements. This is a large number of phonons and so on. So we make several approximations, but it's something that can be done. It was actually already done a while ago in this paper by Hyungyun Choi's group in 2018, where they tried to estimate the TC that might come from the electron phonon interactions in twisted bilayer graphene. Once we have that, we are going to calculate the line width by just using this very standard Midgall the line width formula under the Midgall approximation, and all the objects that we need for this entire calculation just come from the electronic band structure or from the phononic band structure. So with this, we are set, and we can actually calculate the line widths, and we can see whether it makes any sense. So again, we still need to define the Q like the G mode, which we define in exactly the same way as we did for the WSE2, namely that we just take the eigenmodes for the unit cell and we just impose it on both the layers. Now, one of the things that we would like to compute here is we want to compute the line widths, not just the position of the line. So we sort of have to define a spectral function, which is defined in the following way. If I didn't do any projection, I would just take every phonon mode, and if I have the line width for corresponding to that phonon mode, I would just construct a Lorentzian for that particular mode. But now, because we are looking at the projected mode, we actually have to do some projections onto this. It's just a simple technical thing, but it's important because once you do that, essentially, if you look at just the projections, you see exactly what I had shown you before. You see that the projection weights are sort of increasing as the angle decreases. Not the projection weights. The projection weights are what they are, but the spread is increasing as the angle decreases. But something interesting happens when you construct the spectral function. You start seeing that there is an overall two-peaked structure in the spectral function, right? This was kind of unexpected. We thought, we'll see one big peak, which is sort of what had been implied by previous experiments. So we were a little bit surprised by seeing that there are actually two peaks in when you fit the spectral function, and you can of course fit them and get your line width, overall line width from here. When you look at the overall line widths, they are of the order of, they go from anywhere from 16, 17 to about 10 centimeter inverse. And this is for various dopings and, for different angles, near magic angle. One of the line widths for the EG plus mode, which is the higher mode, the line width is higher than for the EG minus mode. There are some peaks here and there, and then you start worrying about, is this numerical artifact? Is this real? And once you start if you look at this peak in careful detail, you realize that this really comes from, the joint density of states is actually increased at this doping, and which is the reason why you actually see this peak. So you can actually explain all of this just in terms of simple joint density of states kind of an argument. Okay. So, but now the question is, where is the split coming from? And if it works once, you try it again, which is the following. We again try to decompose the phonon eigenmodes into different regions and see whether this is something that makes sense. This time we are doing a little bit the decomposition not just in terms of SP regions, which were the sort of the domain walls. We sort of define the domain walls also as between AA and AB and AB and AB differently. We call it SP1 and SP2 and see whether it makes any difference or not. And indeed, you again see that the phonon modes are actually localized very differently in all of these regions. And indeed, you see that some of these modes, are pretty strong in the AB region, whereas other modes are equally strong, are stronger in the SP1 region, right, or in some other regions. So again, the argument still carries through. At least that's what we think. But the other thing is that the real line widths were much larger. So you have to now. This was just the electron phonon part. What about the phonon part? So for that, we actually what we did is. For that, what we did is we actually computed the anharmonic contribution as well. And because we are doing force fields, we can actually compute the velocity autocorrelation, the velocity autocorrelation. But here we will have to do it a mode projected velocity autocorrelation where the mode is defined exactly in the same way. Once you do this, you start seeing that there's an anharmonic contribution as well, which also shows the two-peak structure, which you can fit again to you can fit and you actually get a line width out of all of this. So when you put it all, here on the other hand, if you look, as a function of temperature, this is just the phonon part. There's no electrons as far as this is concerned, right? You see a systematic reduction in the Raman frequency as a function of temperature. So the position is shifting to the left, but also so should I share my screen again? Okay. So as I was saying, the frequency changes as a function of temperature. The position of the peak changes as a function of temperature, but the line widths are more or less the same. They don't really seem to change too much with temperature. Now this doesn't work. I'll just skip through it. That's okay. I'll just skip through it. So then we started wondering. You do theory, you get something, and then you wonder whether this is actually true. So we actually went to our experimentalist colleagues Anindya and Darshit, and they actually measured the Raman spectra near magic angles, and indeed they saw clear splits, which we think are attributed to the reasons that I just discussed. So to conclude, essentially what I've shown you is phonons in Moiré systems can get significantly modified and hybridized because of interlayer interactions. I showed you low frequency phonons, and there are some interesting new effects like phasons which show up in these systems. And both the high frequency Raman modes in twisted WSE2 and the Raman active G modes in twisted bilayer graphene, not only show an increased line width, I mean in the graphene at least that's what we calculated, but also they split because of the fact that the modes coming from different regions actually have different energies. And with that, let me just thank the people who actually did the work. Most of the work that I talked about was done by Indrajit Mehti, who's now at, actually, I don't know where he's now at. Has he moved to Germany? Okay, so he's working with Engel Rubio now, and by Shinjin, who's now graduating and going to move on soon, and with Prabal and Professor H.R. Krishnamurthy, and these are the computational resources. Thank you all for your attention.
Time for questions.
Thank you very much. I had a question or maybe a comment about the incommensurate Phazon mode, because there's a little bit of a subtlety about the Frenkel-Kontarova model, which you can think of if you take a system where you have two commensurate phases near to each other in one domain wall. And then the question is, does the domain wall know where it wants to be on the lattice? Okay? The Phazon limit, of course, it doesn't know where it wants to be. It can move uniformly. But it turns out that, but that's a bit of a surprise, really, because it's discrete. It's sitting on a lattice, it should know. And there is, in fact, a transition which was described by Aubry a long time ago, which he called the transition by breaking of analyticity, whereby if the interaction strength is big enough, it does pin, right. And if it's not, it's stuck. So does that extend to 2D? Does that affect the superlubricity? And you know, can you actually model it in your case?
So that's a very interesting question. Indeed, I mean, there is, so I guess you're referring to the commensurate to incommensurate transition in these systems?
Well, no, even if it's incommensurate,
right.
It can still be pinned.
It can still be pinned, yeah. So one thing that, one thing that we did is in these systems is we raise the temperature, right? I mean, we're doing these classical simulations, so we can just raise the temperature and ask whether the boundary, which basically would be the solitonic boundary, so to say, whether it actually moves, you know, or whether it diffuses out or what happens to it. It actually does seem to vibrate, you know, it moves as a whole, but it seems to go back and forth as one unit. So it certainly doesn't seem pinned, but that could be, you know, related to how strong their interlayer potentials and so on, those things are. And these are usually very weak compared to, let's say, the bond strengths in plane, right? Those are the springs that, there's a K by V ratio in some sense, yeah.
I mean, I guess the point is that you can change that simply by pressure.
That is correct, that is correct.
Then there should be a critical point where
it would, that is correct, yeah.
So to continue on this question, basically there is a connection to superlubricity, but you are also calculating the anharmonicity, which should be somewhat related. When the layers become soft, they can adapt themselves, and then the Phazon mode can be gapped. So do you see any connection between anharmonicity and?
So we hadn't analyzed the anharmonicity in that way, but it might be connected. So I mean, this is not, you know, there's also out of plane displacements here in this model, which probably shouldn't make too much of a difference. But you know, at some level, for the boundary to move, there has to be some out of plane displacement which has to follow this this entire thing. So we haven't analyzed it in that sense, but that's an interesting idea. One you know, we could look at it that way and see if there's something. Yeah.
I guess my question is also on the same theme. So I was thinking about why, you know, when we do, let's say, an AFM measurement on something that's twisted at some reasonable angle, it doesn't slide everywhere, right? It looks right. just as happy as it is.
Right.
And I was thinking back to what, maybe I'll say it my experimentalist way, that at the atomic level, the thing is really stuck. So even though there are places where it wants to slide and places it doesn't want to slide.
Yeah, no, but you know, the thing is, I mean, from what I understand from all experimentalists, you never heat your sample afterwards, right? You never heat it because then the angles change and the layers move around. So there could be defects which could be pinning it, or it could be as you know, there could be some reason that these are pinned because of the fact that you know, the potential is deep enough and it sort of stays there. It could be either one, you know, but you know, in our calculations, these modes do come out to where they come out, and they come out pretty naturally.
Yeah, it's a good point, because in TMDs, actually, if you heat them up, nothing much happens. They stay the same way.
I see.
It's very different from graphene.
Yeah, in graphene, for example, if you heat it up, then things move around, and
Yes, absolutely.
yeah. So it's not, so it's not clear whether this is related to defects or it's related to something intrinsic between the two layers, it could be either one.
But I wonder if you can look locally at regions which are unstable stacking versus stable stacking.
Right.
Whether one can say something from deformations locally of those
Yeah,
regions.
perhaps, yeah.
If not, then let's thank Manish for this very nice